All right, so 45 minutes? Is that
Yep.
45 minutes? Okay. So there is this is a pretty detailed talk. This goes through two of the projects that I worked on in my PhD. It's likely that we'll just focus on part one based on, it sounded like some responses in your WhatsApp group. It sounded like that might be the more interesting topic. And I really would like people to come away with an understanding of what actually happened in this work. So I don't know how these talks are normally run, but I usually like to do my talks where anybody can interrupt with questions at any time. So let's start with that being the rule. Put your hand up if you have a question. I'll take any question at any time. If there's too many questions, I might have to pause questions for a bit. But I think, my goal is to make sure that the maximal number of people do not get lost during this talk. And it will be easy for people to get lost. So please ask questions when you get confused. Okay, yeah, so thank you for the introduction. I'm Gus Smith, and I just finished my PhD at the University of Washington. Reshab is actually a PhD student there right now. He sat next to me. That's how I know him, and that's how I know this group. When he found out I was coming to India, he was like, oh, you should go give a talk at the group I started. And now I'm here. It's great. So, I'm here to present the work that I presented for my dissertation a few months ago. And this work is going to be told through the lens of two projects, Lakeroad and Churchroad. And we may just talk about Lakeroad. I think that'll be the more interesting thing to talk about anyway. And I'm going to try to keep my accent to a minimum so that I'm comprehensible. So I apologize if my American accent's coming on too strong. So here's the overarching story for this talk. Hardware compilers have issues. In our case, I'm going to be talking about hardware. I'm going to be talking about FPGA compilers. And then we're going to talk about how a specific technique from the field of programming languages called program synthesis can help fix those problems. Then in the second part of this talk, we'll talk about how program synthesis itself has issues and how another technique from the field of programming languages called equality saturation can help. So this first half is about a tool that we call Lakeroad. It is what's called a technology mapper for FPGAs. And the second half is an extension of Lakeroad, kind of the second version of Lakeroad, a tool that we call Churchroad. Again, I think we're really going to focus on the first half on Lakeroad in this talk, just based on time restrictions. So with that, let's go ahead and jump into Lakeroad. So Lakeroad was published at ASPLOS 2024. That QR code goes to the ASPLOS talk. So if you want to see a more polished version of this talk where I was much more well rehearsed, you can go ahead and look at that link or take a look at the paper. So at a high level, the story behind Lakeroad is that hardware compilers have issues, but a technique called program synthesis can help fix those issues. And if you don't know what program synthesis is, don't worry. We'll go over it in this talk. I'm hoping that's one of the things that you'll get out of this talk is a high-level view of what is this technique called program synthesis. It's a very fun, fancy thing that people in my field use, and I would love if it was used outside of the field. Before we start, Lakeroad represents more than 2 years of work from my team at UW. So thanks to all these people. All of them, most of them have now moved on from UW, but we had a good time working on this, and they all contributed a lot. So with that, let's jump into it. FPGAs, or field programmable gate arrays, are a popular reconfigurable hardware platform. You don't have to know too much about hardware to understand this talk, I'm hoping. Let's just kind of describe FPGAs at a very high level. So inside of FPGAs, FPGAs are composed of these tiny little hardware primitives. So for example, lookup tables, or LUTs, implement logic functions like and or any composition of logic functions. So if you want to make a logic circuit, you can string a bunch of LUTs together and build that logic circuit. Registers are little devices that hold state. So if you want to hold a value through time, you'll use registers to hold those values. So you can build memories out of registers, things like that. And then these LUTs and registers are kind of the basic building blocks in FPGAs. You can make whatever circuit you want with just logic functions and registers. But FPGAs also contain these specialized units to accelerate common operations. So for example, multiplication. they have built-in multipliers that are contained within these DSPs, or digital signal processors. And these DSPs accelerate common operations that people might want to do. So for example, if you're trying to build a machine learning accelerator on your FPGA, you're going to be using the DSPs a lot because they have built-in multipliers that are very fast. A key step in the process of compiling an input design, so for example, a design written in Verilog or a design written in a higher level hardware design language, a key step in compiling that design down to an FPGA is called technology mapping. And it is the process of technology mapping. It's during technology mapping where we choose what subset of those small hardware primitives we're going to use to implement the input design. So we have some high-level input design, and technology mapping is the process that says, I'm going to use, this many LUTs and this many DSPs configured in this way to implement your design. So to produce an optimal compiled design, it's crucial that we efficiently use the primitives on the FPGA during technology mapping. So we specifically want to take full advantage of the specialized units like DSPs, because if we can use DSPs, we're going to have a smaller, faster, lower power design. However, we have found that when mapping designs, state-of-the-art technology mappers often do not efficiently use primitives. So, for example, imagine that this design could be mapped to a single DSP if the DSP was configured in the correct way. We have found that the state-of-the-art technology mapper, for example, from Xilinx, might fail to discover a mapping to the DSP and instead use additional LUTs and registers on top of that DSP. So these completely unnecessary extra resources. And this leads to a larger and slower design. These mapping failures are exactly the issues that I'm referencing in this overarching story. And in response to these issues, in response to finding these issues, we built a tool called Lakeroad. The key insight of Lakeroad is to apply a technique called program synthesis. Again, I'll talk about what program synthesis is in a bit. But for now, let's just take a look at where Lakeroad fits in this picture. So we already saw that using the state-of-the-art tool from Xilinx, you try to map this design, you end up with a design with that uses extra resources. So we introduced Lakeroad, and by applying program synthesis to technology mapping and producing Lakeroad, we have built a technology mapper that is more complete than existing tools. That is, by more complete, we mean it finds more mapping opportunities and it produces smaller compiled designs. While at the same time, in addition to being more complete, it is also it provides stronger formal correctness guarantees. So we can kind of give you a certificate that your compiled design is correct. And it is also more extensible than other tools. It's easier to support new FPGA architectures with our tool. So we'll dive into the details of how Lakeroad is implemented soon. But first, I really want to dive into exactly the types of issues that we're looking at in hardware compilers. So I want to really go into detail about what these issues look like. And let me get some water before we continue. I got a little bit of a sore throat, so I'm hoping I don't lose my voice during this talk. Okay. So we claim that state-of-the-art tools fail to use existing primitives efficiently. Let's look at a really concrete example of how exactly tools fail and use extra resources, and how do they fail. So let's imagine, and again, if you've never seen Verilog before, don't worry. We're not going to look at a lot of Verilog. You don't need to understand it in detail. But let's imagine that a hardware designer is trying to compile this design that's shown on the screen. And this design is very, very simple. It just does what it says it does. It does an add, a multiply, and then an AND. Or sorry, an add and a multiply and then an add on 4 different inputs. And you can see the visualization of the circuit there as well. So they're trying to compile this design onto a Xilinx UltraScale Plus FPGA. The UltraScale Plus FPGA architecture, like most FPGA architectures, contains plenty of LUTs and registers, which I said are the basic building blocks, the logic units and the state elements that you can build any design out of on an FPGA. But for maximum performance, our hardware designer is instead aiming to use the architecture's specialized DSP primitives. Again, DSPs are built exactly for this kind of multiplication workload. So they really want to use these DSPs to make the thing fast and small and power efficient. They know that if programmed correctly, the UltraScale Plus DSP, called the DSP48E2, can efficiently implement their design. So if the DSP specifically is programmed to select the pre-adder, the multiplier, and the post-adder, it will implement their add, multiply, and design. So then we would expect that if we try to compile this design with Xilinx's tools, the tools should say that we can compile this design using just a single DSP. We should be able to implement this design using just a single DSP if we can figure out how to compile, if we can figure out how to configure the DSP correctly. However, when we actually attempt mapping with Xilinx's proprietary state-of-the-art compiler, and I've been calling it Xilinx's proprietary state-of-the-art compiler because I'm not actually allowed to name it in the paper for licensing reasons. It's called Vivado. You may have heard of it before. We couldn't write that in the paper because they might come after us because you're not allowed to benchmark against their tools, which seems a little bit crazy. Sorry if anybody's from Xilinx in this room. Apologies, or AMD, I guess, the parent company. So when we actually attempt a mapping with the state-of-the-art tool from Xilinx, we find something odd, which is that the compiler produces a design which does in fact use a DSP, which is what we expect, but it also uses extra LUTs and registers. It uses these extra resources, and these are completely unnecessary. And you may say this example is just a toy example, it's just an example that I cooked up, but it just takes a little bit of Googling online to find people running into very similar issues. On the Xilinx forums or on Reddit, you'll find people who are experiencing similar mapping failures. It's a very common problem. So the state-of-the-art tool has failed us. Now what? What do we do now? Do we just give up and accept suboptimal results? Well, a lot of hardware designers will actually be forced to just accept suboptimal results because they won't really have any other avenue. They don't know how to compile their design in a more efficient way. They're stuck with this tool that is just giving them these suboptimal results. The only other option, if we want to get this optimal design, is to manually instantiate the DSP. And by manually instantiate, I mean that our designer has to handwrite Verilog that will instantiate the DSP in the way that we want. And this is kind of, I think most people in this room are probably software people. The analogy here is, you're writing C++ code, but then you have to go and write inline assembly to produce the exact optimal code that you're looking for. And this is, inline assembly is mostly a thing of the past, thankfully for people, other than, very, very low-level people. But in hardware design, the equivalent of inline assembly is very, very common. It's very common to now have to go and manually instantiate these primitives by hand. So to make it really concrete, here's an example of the Verilog that you'd have to write by hand if you wanted to instantiate this DSP. And you don't need to understand Verilog to see that you wouldn't want to write this by hand. You would not want to be tasked with having to write this. And that's partly because each of these lines in this DSP instantiation is a separate port or parameter of the DSP, which you have to determine how to set by reading through Xilinx's manual for the DSP, which is 75 pages long, and it contains all of these, crazy, complex, interdependent constraints between the port and parameter values, which makes, all in all, makes configuring a DSP by hand very difficult, very confusing. And believe me, I've done it, and I know that manual back to front, and it's not something that you want to do. Even once our designer has gone ahead and written this implementation by hand, and they have a design that finally uses just a single DSP because they built it by hand, they still have no formal guarantees that their output is correct. And by formal guarantees, this is kind of language from the field of programming languages and verification, but really what I mean is mathematical proof that their design implements, that their compiled design implements their input design. A kind of a machine-checked proof that this compiled output does exactly what their input said it should do. So they can attempt to catch bugs via testing, which is a classic and well-used method for catching bugs. But there's no way of knowing that they've found every possible edge case or that they didn't miss some edge case buried in the manual somewhere. So to recap where we're at this point. State-of-the-art tools failed to produce an efficient mapping. Because our designer wanted this, optimal mapping, it cost them a lot of time and effort to go ahead and program it manually, to write out that instantiation manually. And finally, once they have that implementation, they don't even know if it's correct. They have no certainty that what they've written is correct. But let's step back a little bit and look at this process. Look at the process we just went through. So to configure the DSP, our hardware designer had to write all of this strange, esoteric syntax by hand. To do so, they needed to consult extensive documentation, and that extensive documentation documents which ports and parameter values are legal and which ones aren't. So given all that, it's really starting to sound like configuring a DSP using Verilog is a lot like writing a program in a very small domain-specific language embedded within Verilog itself. So there's kind of like a language embedded within the ports and parameter values of the DSP. And they are just trying to figure out which programs or which settings of the ports and parameters are legal and which ones are not, and which settings will do what they want it to do. So like I said, configuring a DSP is a lot like writing a program in a domain-specific language embedded within the port and parameter values themselves. And this realization brings us to our main insight. Oh, did not mean to do that. Hang on. Uh-oh. Hang on. I just killed the presentation. Are we good? Okay. Okay, so this realization brings us to our main insight. So configuring DSPs and other complex primitives, like I said, is very similar to writing a program. So we should go ahead and use a technique from programming languages called program synthesis. This technique is very good for doing this. Yes. So are you saying, did we find this in FPGAs, like non-Xilinx FPGAs? Yes. Yeah. So I'll show some results at the end where we test on 3 architectures in total, and with 3 different tools, and we show that all tools have these mapping failures. And our tool, that I'll introduce in a bit, is able to map more than what their existing state-of-the-art tool can map. But I'll get to that in the evaluation. Okay, so I've talked a lot about program synthesis. So what actually is program synthesis? And again, I think that this is probably one of the most interesting parts of this talk. This specific technique it's really useful in certain circumstances, and I wish it was broader, known more broadly. So we're going to go ahead and move on from talking about our problem, that is, the mapping issues that we just covered, into talking about the solution, which is applying program synthesis. So at a high level, Lakeroad is a tool which takes an input design in Verilog, uses program synthesis to compile that design down to a low-level design, which strangely enough is also in Verilog, but that's just a hardware design thing. In Verilog kind of has multiple languages embedded inside of it. You have a high-level language and kind of an assembly-level language. So it's not weird that it's going from Verilog back to Verilog. So Lakeroad takes in this high-level Verilog, uses program synthesis to produce a low-level implementation. So let's go ahead and see how Lakeroad uses program synthesis in its implementation. So internally, Lakeroad is using a specific type of program synthesis called sketch-guided program synthesis. And sketch-guided program synthesis begins with, unsurprisingly based on the name, something called a sketch. A sketch captures what our compiled design should look like, kind of like a scaffolding that's going to have these holes in it. You see these holes marked on the screen. And so we've now scaffolded what the output should look like, what we are expecting it to look like, but we have left open these holes that we are going to essentially fill in, or we're going to allow something to fill in. So yeah, crucially, sketches, they scaffold the output result, but they have these holes that will be filled in by an SMT solver. And if you don't know about SMT solvers are essentially just these very, very high-powered tools that can solve constraint problems. So if you've ever heard of the SAT problem, like 3 SAT or just SAT in computer science, it's a classic problem of you have some set of clauses that you're trying to satisfy. You're trying to make them true. You're trying to find an assignment to variables that makes it true. SMT is kind of a SAT, SAT modulo theories is what it stands for. And it's essentially an upgraded SAT that allows you to add new data types and things like that. But you don't have to worry about how SMT works. All you have to know is it's a solver that takes constraint problems and solves them for you. Yes?
How much it only can synthesize APIs?
Yes. Yeah.
Are these tools, they're also going to, the constraint solver is only...
They're going to be bit vectors. They're going to be fixed with bit vectors. But that's okay, because in Verilog, I mean, the basic data type in Verilog is a fixed width bit vector. So if you think about it in hardware, everything is essentially a fixed width bit vector, because you either have a single wire, so a single bit, or you have a wire that's a bundle of bits. So everything in hardware is, the sizes are all known. So that's the fixed, what I mean by fixed width. And it's all just, it's all bits. It's all ones and zeros. So we don't even actually need, it's called the theory of integers. We don't even actually need the theory of integers. We just need the theory of bit vectors, which is a much easier theory that actually makes the solvers run a lot faster, surprisingly. Yeah, good question. Any other questions? Yeah. Mm-hmm.
So is there any particular reason why sketch guided synthesis
So sketch guided synthesis actually does use under the hood counterexample guided synthesis. It's a great question, and I won't talk too much about it, but in a second or two, I'm going to show like calling out to a solver and getting a solution back. Inside of that solver, you can think there is essentially a counterexample guided synthesis algorithm that's running. And so for people in the crowd, there's many different types of synthesis. Synthesis at a high level is just trying to solve a problem using a solver, and there's many different algorithms for it. And one of the common ones is counterexample guided synthesis. Essentially just saying, asking the solver a question, it gives you back a result. That result might actually be wrong. If you find a counterexample, where the result is wrong, you can also say, hey, solver, find me a new solution and make sure it's correct in the case that you got it wrong in last time. We could talk about this offline afterwards. I'm happy to talk more about synthesis in detail. Other questions?
What is verified in that case? For example, synthesis requires verified. What verified what you have?
So we could talk about it during the results, but I use 5 solvers total. So we're using, what is it? CVC5, Bitvuzla. Basically all of the most popular open source SMT solvers is what I'm using. Yeah.
No, I thought there is but this problem you have a domain specific verified. So
Yep.
you use standard solvers.
Yes, yeah, we use standard solvers. Yeah, standard SMT solvers. We could also talk a little bit more offline about how this is structured internally, because there's some details there. Okay, so we have our sketch, right? This is now capturing what the output should look like, and it has these holes in it. So now what do we do? Well, what we're going to do, like I said, SMT solvers are constraint solvers. You send them a set of constraints, and they try to satisfy those constraints for you. So what are we going to do if we want to use it as a compiler? Well, we're going to create a constraint. So we're going to assert that this sketch is equal to the design that we're compiling. In this case, our add, multiply, add. So we're actually just creating this statement. Is the thing on the left, the DSP instantiation, is that equal to our input design? Can you make an assignment to these holes that makes this true? And then we go ahead and query the constraint solver, something like CVC5 or Z3. There's a bunch of open source SMT solvers out there to determine if there's any way to fill in the holes to make this true. And if there is a solution, this constraint solver will go ahead and return that, and we can use that solution to fill in the holes in the sketch. And once we filled in those holes, we can go ahead and just return that as the compiled design in Verilog. So essentially we are calling out to the solver to figure out if there's a way to configure this DSP for us. And because we generated this implementation using this constraint solver, if you trust your constraint solver, then you get a strong correctness guarantee. And this is really one of the best things about using these solvers is that they're very heavily used, very well trusted across the industry. And so, you can essentially guarantee that this constraint that you sent in is satisfied. Whatever comes out correctly implements your input design. Yeah. So it doesn't guarantee optimality. This is not guaranteeing optimality. The nice thing about using it in this case is that if you can map something to a single DSP, that's usually assumed to be optimal. That's a very broad statement. It depends on the input design, but generally, if you can use a single DSP versus a DSP and a few LUTs, one DSP is always better.
Yeah, not emphasize, that means DSP is not enough.
Yes, yeah. So, and we'll talk about this a little bit more in the results, but that's the other neat thing here is that because you are using a solver, and if the solver can say, this is not possible, and in that case, with 100% certainty that the DSP can't actually implement that design. So you kind of get it's not just like a vague compilation failed message. It's no, this is actually not possible. Okay. So to implement this, we're using a language called Rosette, which I highly recommend you look into if you have any curiosity about program synthesis. They have great documentation. It's a very, very fun tool to use to learn about program synthesis. It was developed heavily at UW. Now it's mostly maintained by external people. So we don't have that much time to dive deeper into implementation because I want to talk about results and a little bit of future work. But there is one really neat technical detail here. And don't worry if this is not comprehensible. This is a little bit in the weeds, but it's also my favorite part of the whole work. So I like to throw it in. So one thing to note is that an SMT solver, yeah.
Basically, you're saying each primitive
Mm-hmm.
will have a constraint number which you define.
We don't even have to define it per primitive necessarily. Actually, this might make some sense to you. If you wait, this might answer your question. But you don't have to implement anything per primitive because I'll explain it in this slide. So the solver, an SMT solver speaks a very specific language. It speaks a language of constraints, and it's honestly not too hard to understand. It's essentially just assertions over bit vectors. Like I could say, I have A, which is an 8-bit number, and I have B, which is an 8-bit number. Find a assignment to those numbers such that A is greater than B. Basic stuff like that. Really not too hard. So that being said, a solver doesn't understand Verilog. So, in this previous slide, I showed us saying, this Verilog on the left is equal to this expression on the right. The solver can't actually understand this Verilog syntax. That doesn't make sense to the solver. So, how do we make the solver understand what the primitive does, what a DSP instantiation means? How do we bring that instantiation down to a level that the solver actually understands? So yeah, like I said, the solver doesn't actually know what this syntax means. Well, luckily, Xilinx and really any major FPGA company that builds an FPGA releases models of their primitives, usually in Verilog. These massive Verilog files encode the exact functional behavior of these primitives. And so these are usually used for post-synthesis validation. So let's say I'm trying to build a design. I run it through Xilinx's compiler. They map it down to DSPs, and then I'll go ahead and run simulation on that compiled design. And the simulation will use these models to essentially produce, to simulate what the hardware will do. So they're really meant for post-compilation validation. But what if we use them to actually build the compiler itself? There's no reason we can't use this file to essentially automatically generate our compiler, right? So this file encodes exactly what the DSP does. So can we extract out the meaning from this file and generate our compiler from that? So Lakeroad introduces a technique that we call semantics extraction, which utilizes the open source hardware synthesis tool called Yosis to essentially convert that big blob of Verilog down to semantics that are comprehensible to the underlying solver. You don't have to understand what's happening on the right. Just know that that syntax is a lot more friendly to these solvers. The solvers can actually understand what the thing on the right. So we've converted this big blob of Verilog down to something a solver can understand. And now we can ask the solver, can we implement this design using this hardware block? Because the solver can now reason about what the hardware block does. So, like I said, I think this idea is this is the most exciting component of this work, is this idea of, given just a simulation model, or given a hardware design file for a specific block, you can actually go ahead and generate a part of your compiler for that block, just given those semantics. And you could take this into the world of software too. There's no reason you couldn't have, a specialized part of your CPU, take the design files for it, and generate a piece of your compiler that targets that specialized unit on your CPU, something like that. Okay, so let's jump into evaluation. But did that answer your question? It was good. Okay, good.
What happens if solver fails?
So we'll talk about that. There's two ways a solver can fail, and that will come up in a few slides. So I'll ask me again if it doesn't answer your question. Any other questions before? Yeah.
Component synthesis.
So I don't think I know what that is. What's component synthesis?
You can just heat up these parameters. You can take as an operation.
Mm-hmm.
All you need to do is kind of come up with a sequence of. You need to discover the sequence.
So I think I see what you're saying. The problem is that something like if you want to treat a DSP as a single operator, how do you capture what that operator can do? Because a DSP can do so many things, and it has 100 parameters essentially, and those parameters have many different combinations of values, and every single way you can configure the DSP, it does something slightly different. So if the idea is essentially represent the DSP as an operator, then the question is, who is writing down exactly what that operator does? And the thing that I just showed, this semantics extraction, the core idea is, well, if you're going to write down the DSP as an operator, somebody has to tell you what it does. Why don't we just use the simulation file? The Xilinx engineers already wrote out what it does in a 2,000-line Verilog file. So they already did the work to tell us what the thing does. Let's just take their work and generate our compiler out of it. They've done the work for us. So we could talk a little bit more offline, because I don't quite know what component synthesis is, but I think the core question is, somebody has to say what the thing does. And this is kind of the ground truth model to start from, is my argument. Okay, let's talk about evaluation. So we evaluate Lakeroad on the axes of completeness, correctness, and extensibility, and I'll talk about what each of those means. So completeness, by completeness, we mean that Lakeroad finds more mappings than other tools. So recall that, let's go back to that original example that we were looking at. Remember that the state-of-the-art tool from Xilinx maps the design using extra LUTs and registers. So it doesn't successfully map it down to a single DSP. It uses extra resources. While, as we showed, Lakeroad is able to successfully map it to a single DSP. So we get the green check. We're good. We've mapped it to a single DSP. Well, to evaluate this completeness claim, in which I claim that Lakeroad finds more mappings, we're essentially just going to expand this example. We're going to add a lot more designs to compile. And we're also going to add other tools to compare against. So, one thing we do is we add Yosis, this open source hardware design tool. We're also going to compare against that. So every design that we evaluate, we'll run it through Yosis as well, and we'll see, did it map it to a DSP or not? And then we also expand the number of designs. So what we do is we look at the documentation for the Xilinx DSP, and we say, what does this documentation claim can go onto a single DSP? What is the documentation telling us the DSP can implement? And based on what the documentation says, we enumerate we just have a Python script that enumerates a bunch of hardware design files, each of which should be able to fit onto a single DSP according to their documentation. And that, yes, like I said, each of these should go onto a single DSP because we generated it from the documentation. And that gives us a set of about 700 benchmarks. And so we're going to run each of those benchmarks through each of our 3 tools, and we're going to, check whether the tool is able to successfully compile it to a single DSP or not. Again, like I said, each of these designs should go onto a single DSP. We'll see if they actually do. So let's take a look at the results. We're going to start with Yosis, the open source hardware compiler. Yosis successfully maps about 2% of the benchmarks down to a single DSP, represented by this green bar here. And on the rest of the benchmarks, Yosis fails to find a mapping to a single DSP. In this case, Yosis, it may find a mapping that uses a DSP and LUTs and registers, or it may find a mapping that doesn't use a DSP at all. It always returns a design. It's never throwing an error, but it may return a non-optimal design. So moving on from Yosis, the state-of-the-art tool from Xilinx does a lot better. It maps about half the designs to a single DSP. But again, remember, this is we're claiming that we generated these designs from Xilinx's own documentation. Their documentation claims that these should go onto a single DSP, and yet the tool is only putting about half of them onto a single DSP. So it's kind of a surprising result, right? Like they claim these workloads go onto single DSPs, and yet their compiler is not mapping them. So Lakeroad outdoes them both, maps about 70% of designs to a single DSP. And then this gets to the question about how the solvers fail. So you'll see we're not using red at the top of the bar to account for the failures. We're using purple and black. So let's talk about what those are. So the red in the case of Xilinx and Yosis, those are just, they return as a design that uses extra resources. In the case of Lakeroad, we have these 2 different error cases. So purple, well, let's talk about black first because it's more straightforward. In the black cases, the solvers time out. So sometimes SMT solvers can't find a solution, and so they just spin forever. So we just set a hard timeout. We say, you can wait for 10 seconds. And if you can't find a solution in 10 seconds, we're going to cut you off. So that small bar up there is the cases where we had to cut the timer, we had to cut the solver because it was taking too long. Yeah. So it was different per architecture, but I think for Xilinx it was 60 seconds, I think. We get marginally more the more we increase the timeout, but not that much. It seems like there's some cases that are just, they'll take minutes, hours, or maybe never terminate. The purple case is more interesting. So the purple case is what's called unsat, or unsatisfiable. And this is the case where the solver tells us explicitly, this constraint that you gave us, this compilation that you're trying to do, is not actually possible. You asked us to put this design onto a DSP, and we actually, the solver proves it is not possible to implement this design using a DSP. So that's interesting, right? Because we generated these designs from the documentation. In theory, they should go onto a DSP. So there's 3 things that could be happening here. Number 1, remember, Lakeroad is only as smart as the simulation models that we generate the compiler from. So if that simulation model that Xilinx provides is incorrect, then, and if it doesn't cover certain features of the DSP, Lakeroad cannot learn how to use those features of the DSP. And we already know that these simulation files have bugs. We've seen bugs in them, we found bugs. So it would not be surprising if they were incomplete. So that's one potential reason for unsat. 2 is that the documentation could be wrong. The documentation could claim that the DSP does things that it doesn't do, or is written in a way that we misinterpreted it for sure. We could have misinterpreted the documentation. Very common problem as well. If you've ever read any hardware documentation, it's a precise art writing a manual. Yeah. Mm-hmm.
The logics of this other ones, registers and you able to create the design? Have you done that?
So yeah, so if we provide a sketch that adds extra resources, yes, we can fill in the holes. We can say, like, if you can't use a DSP, you can then use extra LUTs. So yes, that's definitely possible as well. We mostly, we didn't include those in the results because we thought it was more interesting to just look at the cases where single DSP fails, because this entire set of benchmarks should go onto a single DSP. So it's interesting when it fails, right? It's interesting when that's not the case. And the third case is that we actually also add some additional constraints to try to reduce the number of timeouts. So to reduce that black bar at the top. And those constraints should not cut out useful cases, but they may. We may have an error in the constraints that we've provided to speed up synthesis. So, it could be the simulation model is wrong, documentation's wrong, or our provided constraints are wrong. So we haven't looked into, we need to look into more where these unsats are coming from, but those are the three cases. Yeah.
Can you also provide other resources?
Yes. So going way back to the sketch, and actually I'll talk about this in the future work too, but the sketch really gives you the scaffolding of what the output looks like. If a resource isn't in the sketch, then the solver won't add the resource in. But if, for example, your sketch says, here's a DSP, and then it also has a few LUTs after it, then it can use those LUTs and it can configure those if it needs them. So it's all about what you put in the sketch, basically. Yeah, so whatever you put in is exactly what it's going to use. There's a bit of, you can be a little bit more clever with it. Sometimes you can say, like, here's a block of hardware that you can choose to use or not, and if you don't choose to use it, then leave it out. But for the most part, what's in the sketch is exactly the resources that are going to be used. Yeah. Yeah. Yes. Yes, absolutely. So you can, and that's the nice thing about Rosette as well as the tool that we're using. It makes it easy to do those kinds of. So the question was, can you use something like weighted max sat? There's a bunch of, there are a bunch of solver algorithms that also allow you to specify optimization constraints. The one thing I will say, but we tried it a little bit. The one thing I will say about it is it always makes the solver slower, and we're already running up against timeouts. So when you're pushing a solver to its limit, adding more on top is always going to make it timeout more often. But yes, it's definitely possible to use that to, actually show our design is optimal or give it more flexibility to use more resources if it wants. Yeah. What do you mean on what, like? Oh, yeah, I forgot the numbers. They're not in this talk. We did a long time ago. We looked at like the actual number of constraints we were generating, but I lost it now. We provided some benchmarks to the CVC5 team from this work so that they could use them because we produced some pretty large problems. But now I've lost it. I don't remember. Yeah. So I think there was, again, I'm kind of forgetting because this was a while ago. There was at least one case where we tried it because we were like, this is really weird. The documentation says this is possible. And it turns out it was because we missed a line in the documentation. So there's a line about how you can't use the multiplier and use logic functions like and or at the same time. And we just missed, there was like one line in the 75-page PDF. And so going through the process of mapping by hand is what helped us find that. But yeah. So that is always a useful exercise. Let me go ahead and finish this up quick because I do want to talk a little bit of future work that I think is, it's LLM stuff, so it's always interesting for people who like AI. These results hold across, somebody asked about other architectures. We evaluated on 3 architectures. These results hold across all 3 architectures, so Lattice and Intel or Altera. So that's the completeness claim. Basically, we produce more mappings. We find better mappings than other tools. Great. I'll just zoom through correctness. Correctness is easy. Our claim is that we provide stronger correctness guarantees. And that's because the tools we compare against don't provide any correctness guarantees. So it's easy to beat them on that. Because we use a solver, we actually can prove to you that we satisfy the constraint that your output design is equal to your input design. Yeah, so we use synthesis and solvers, and that gives us correctness. Extensibility, this is basically just the fact
proof agent.
No, so yeah, I'm being a little loose with the terminology here, but the essentially, I guess the solution to the solution plus the set of constraints is your certificate. But if you really wanted a proof certificate, you'd have to, I think you'd have to probably simplify the results a little bit more. But more so, what I mean is you get a checkable set of you get a checkable constraint and set of values to fill into that constraint, essentially. Any other questions on correctness? Okay. So extensibility, our claim is that we more easily support new FPGAs. Again, this is partly an easy claim because something like Vivado only supports Xilinx FPGAs. It's not an extensible tool. But the fun thing about Lakeroad is because we do this semantics extraction, if you have a block if you have Verilog representing your, for example, your DSP on your new fun FPGA, all you have to do is throw that into Lakeroad, and it can extract the semantics from that simulation model and be able to compile to your FPGA. So this is really what we mean by extensibility. If you want to support your new FPGA, you just throw in your simulation models, and our compiler will work for you. So that is, I'll just stop. I'm going to just do the Lakeroad portion. So the overarching story here is hardware compilers have issues. That is, state-of-the-art tools do not efficiently use primitives. And program synthesis can help. And using program synthesis, we built Lakeroad, which finds more mappings than other tools, among other things. I want to talk really quickly about some future work. Sorry, I'll just go 5 minutes over. Sorry about that. So a fun piece of future work for people who like LLMs. I was talking to some people who do LLM stuff, so I wanted to include this. So currently users have to provide those sketches that I was talking about. We only saw one sketch, which is just a single DSP, but you could make sketches as complex as you want. And to compile to more, if you want to generate more complex designs, you have to make a bigger sketch. So if we don't want the user to have to provide those sketches, why don't we use LLMs to generate these sketches? This is what they're good at, is generating code. So yeah, like I said, a core requirement for Lakeroad and Churchroad, which we didn't talk about, are sketches, which define the search space for the solver to search with it. So imagine, a bigger sketch than what we thought of before. So this is a 2 DSP sketch. We're actually combining two DSPs together and wiring them together in a certain way. But we still have these parameters, these holes that are going to be filled in by the solver. The solver isn't actually able to explore other sketch structures. Whatever you give it as the sketch, that's its search space. It can't add new DSPs. It can't add LUTs, whatever. If you want to do that, the user has to do it by hand. Ignore this thing about Churchroad, but basically, yeah, sketches must be written by hand. That's a problem. So what if we used LLMs instead to generate sketches and then had the program synthesis routine, had Lakeroad fill in those sketches? So the hypothetical flow here is something like, we could prompt ChatGPT with, I have the following hardware design, and then you pass in the design you're trying to compile. I would like you to map it to Xilinx DSP48 E2s. Here are some mapping examples, and then you could provide a bunch of, input-output examples. When you return your mapping, please leave out the parameters of each DSP and replace them with placeholders like P0 and P1. Those are going to be the holes that will be filled in by the solver. And then maybe ChatGPT comes back and gives you the sketch that we saw on the previous page, which would be great because the sketch actually can be used to implement the above design. And then what we do is we take that sketch in and throw it into Lakeroad, and then we ask Lakeroad to say, use the solvers to fill in the sketch. And if that fails, if the sketch won't work, we can always go back and ask the LLM for more sketches. So the nice thing about this approach is that it leverages the benefits of both LLMs and program synthesis. So, what's good about program synthesis? It's, in PL, in programming language terminology, it's sound and complete, which means it can't generate incorrect code, and it will always find a solution if a solution exists. That's great. But it really struggles to handle large search spaces. You have to constrain it with these sketches. So that's a big problem for program synthesis. The pros and cons of LLMs are that they can see patterns easily and they can definitely produce plausible sketches. That's what they're good at, is kind of producing plausible code that is maybe close enough, but maybe not exactly right. But it can't guarantee that the output code that you want is correct. or the output code that it generates is correct. So, if we were to ask ChatGPT to just compile to a DSP for us, we might get valid Verilog, but we have no idea whether it's correct or not. So by guessing with LLMs, by kind of producing the scaffolding with LLMs, and then checking with program synthesis, by actually doing that final step where we fill in the holes with program synthesis, we kind of get the best of both worlds. We get the exploration capabilities of LLMs, and we get the genuine proof of correctness from program synthesis. And I think I'm going to cut it at that because I have more future work, but it's related to Churchroad stuff. So with that, I'll end the talk. Thank you all. Yes, open to questions. Go ahead.
Why not some other techniques from program synthesis?
It's a great question, and this is why I'm sad that I, didn't leave time for part 2, because that's exactly what part 2 is about. So part 2 is essentially, can we generate sketches using some techniques from programming languages by looking at the input design itself? So take a look at the input design and take a guess from the input design how many, for example, DSPs we would need to implement that design and how they should be wired together. And then once we've kind of made a guess, we can turn that into a sketch and then use Lakeroad to fill in. So part 2, Churchroad, is really about essentially looking at kind of like the AST, looking at the program and determining from the program, building a sketch from that, rather than using LLMs, which are kind of a mysterious black box. But yeah, it's a great question. So, like you mean like solver-aided programming by example, that kind of thing? So you could. I mean, there's no reason you couldn't do like a programming by example like thing here. I would have to think about how you'd structure that, but I don't see why not. Yeah, I mean, you could do programming by example. I think you would. The problem with hardware is that like programming by example is good in the case of like Excel, where it's like it's very human interactive. I can see if the thing is correct or not. Hardware, there's so many edge cases. If I'm compiling a module, I really want to know that it's correct in all cases. And there's a lot of cases that I can't even really think about. Programming by example is really, really good for human interface stuff, where it's really easy to tell if something is correct or not. Like building a UI in web design, where I've seen it applied really well. It's like you can see if that UI is correct or not, because it's like the UI is for me. I know what I want. So it's a good thought, and you probably could do it. It would just, I think the worry would be, can you make sure all of the edge cases are handled? Yeah. More questions? Yeah.
I had one question. Once I've written the design, so the designer has to know where I must add these fields that you mentioned, the holes and the sketches, right? The sketches manually, so you must know the resources required for this design and then add it manually.
So for the most part, you don't need to add those holes manually. This is if you want the details on this, I would recommend looking at the paper. But there's a lot of engineering in Lakeroad that essentially hides a lot of that from the user. All they really need to provide is there's a configuration file that they provide that basically says, my architecture has a DSP, it's named this, and it has these ports and parameters. And you just list out the ports and parameters. And those are essentially what are going to become the holes. But you just have to you just put them in a list, essentially. Just give the names in a list. And then Lakeroad will go ahead and automatically instantiate the sketch and fill in the holes put the holes in where they need to go. So the user does need to do some work to write out that configuration file, but that configuration file is done once per architecture. So in Lakeroad, we already have, the basic FPGA architecture is already implemented. And then in terms of sketches, yes, I think providing new sketches is something that I don't ever want a user to have to do. And like I talked about with the LLM stuff or with Churchroad, a lot of the work that I'm doing is trying to make sure nobody ever has to write a sketch. But Lakeroad also has built-in sketches that cover most of the useful cases right now. Because most of the time, what we think people should be using Lakeroad for is configuring a DSP. because that problem in itself, just a single DSP, is very hard. As you could tell from the results, existing compilers fail to do it a lot of times. So, and there's already a single DSP sketch built into Lakeroad.
So, I want to know the overhead of Lakeroad and the complete synthesis costs and your time.
Yes, it's a great question. So it's been a bit since I've looked at it. The results are in the paper, but it's something like on the order of, I think, like the median time for compiling to Xilinx DSPs is on the order of like 3 or 4 seconds. So a pretty long compilation time for a single DSP for sure. And we're trying to get that down using, by using better solvers. The less complex your architecture is, the faster it is for sure. At the same time, compilation in hardware design runs on the order of days for complex design. It's very normal to run your compiler for days, which is crazy to anybody in software, but that's the norm because compiling designs, and especially doing layout optimization, things like that, is just solving very hard algorithms, and it takes a long, long time. So it's, if you're trying to convince somebody to add a 4-second routine into a software compiler, they might not buy it, but for hardware people, it was not a very big deal for them when they reviewed the paper to see that it ran in 4 seconds.
4 seconds for one DSP.
4 seconds for one DSP compilation.
Right. So design might have multiple DSPs.
It might have multiple DSPs, but it's likely to have the same DSP configured the same way many, many times. So you solve it once, you can use it in many places. Yeah.
I have some program that is created and I have some packaging between. Can you fill those spaces automatically?
Sure, yeah. Yeah. So we haven't, that's kind of what Churchroad does in a sense, is it takes your full design and maybe inside that design there's something that should be filled in, and it will just call the solver on that section and fill in those holes. But if you even wanted to provide the entire design to Lakeroad and just have holes kind of somewhere buried inside there, that would be fine too. It can handle that. Yes, so that's all handled by Rosette. There's a symbolic executor built into Rosette, and then we do, symbolically executing the Verilog is really just a matter of converting the Verilog into a language that Rosette understands. There's some details about that in the paper because it is kind of interesting turning Verilog into something that can be symbolically executed, but it's mostly just converting it into Rosette syntax.
I think that usually it's one DSP pattern that repeats
Mhm.
Is it possible to, maybe make a repository of things that you see commonly and have it pre-computed and somehow use that to speed up the computation?
For sure, yeah, like caching common DSP configurations. Definitely, this is actually something we thought about doing because a compiler like Xilinx's compiler or like Yosis, they're not going to want to run program synthesis inside their compiler because it could time out. It's just you don't know how long it's going to take. It takes a while. So one of the things we thought about doing, and we actually proposed this to the Yosis people, is to build a library of patterns that's essentially, if you see this pattern, then map it to this DSP configuration, and just use Lakeroad to generate all those patterns. And we actually have a backend for Lakeroad that generates patterns in the Yosis format. So if you say, I want Yosis to now by default handle map a DSP where you're doing an add and then a multiply and an add, you just pass in that add, multiply, add design, and you say, output to a Yosis pattern, and then you can copy that file into Yosis source code, and it's now enabled. Like now they can map to that DSP. So definitely, yeah, it's a great idea.
How about the compiler optimization?
So the compiler optimization in Yosis it's a lot of this mapping step happens after that optimization anyway. So like this is kind of like last level, and once you map to hardware, you're generally not at least in Yosis, they're not really rearranging those blocks. So at least in their current state, wouldn't be affected all that much. But yeah, it's a good question. Like how it's something you definitely would need to think about. Yeah.
So if you have a project which is already using Yosis,
Mhm.
it's easy to find. We use Lakeroad, we detect
and the verifier in behind to use again and do the mistake.
Yeah. I mean, that would be the hope. Yeah. So we haven't actually contributed any of these patterns back to Yosis. Yeah. So the other thing that we're also trying to do is just provide Lakeroad as a Yosis plugin. So, for example, if you had a big design you're compiling with Yosis, you should be able to annotate certain modules with, a Lakeroad annotation, and then there'll be a pass in Yosis that's just run Lakeroad on all the annotated modules, and then that will compile each of those modules. So, for example, if you have a module that should go into a single DSP, then you can annotate it with Lakeroad. Lakeroad will produce that mapping for you, and you can just use that Lakeroad pass to do part of your compilation in your larger Yosis, in your larger Yosis flow. Yeah. But it's been dormant because I graduated a few months ago and I haven't worked on it in a bit. So I should make the final push to get this stuff merged into Yosis. I haven't done it yet though. So
You mentioned that it's quite common to have workloads running with J's on the end.
yeah.
But is it would it be feasible to maybe use some sort of heuristic to just determine when to give up on your solver and fall back to using what's
Sure. Yeah, for sure. I mean, we currently just set a hard timeout, but there's no reason not to have smarter ways to. Also, we do things like using different solvers. We run multiple solvers in parallel. You could, for example, run a solver, kill it, and run it with different flags to try to, so yes, definitely. There's a lot you can do in the space of like getting program synthesis to terminate. That's a whole problem in itself. So a lot you could do there. Are we out of time?